Hello friends, we are back to read another audit report on Code Arena to learn from previous audit findings. I think I'll be doing these on a fairly regular basis now, since it's also helping me internalize these findings a bit better, just having to explain them in these videos. So we'll be going over the Kali report today. Jumping straight into the first high severity finding, looking at the code in question, the issue is around calling transferFrom on an arbitrary user supplied vault token. It's assuming this vault token is going to be an ERC721, but if you actually look at this logic check here, the token type is actually specified by the user as a user parameter. So the user can actually specify a vault token that is an ERC20 token and mismatch the token type to be an ERC721, which will force the code to run a transferFrom on an ERC20 token instead. Some ERC20 tokens do not revert the transaction when it fails. So when transferring ERC tokens, you always want to check the return value from transferFrom, or use something like safeTransferFrom, where it will actually revert the transaction if the transfer fails. So by creating a vault that uses one of these bad ERC20 tokens that doesn't revert on failed transfers, the function call to createVault will succeed without any errors after executing this line, and we'll be able to create a vault that is actually empty and doesn't have any tokens inside. A simple solution to this issue is just to use safeTransferFrom for both of these vault token types. And that'll make sure an attacker won't be able to create an empty vault that could trick a user into bidding for it and not receiving anything back in return. I actually talked about this finding in a bit more detail in a previous video, where I gave a bit more background in how I went about spotting this finding during my audit. So check out that video if you want a bit more background on this. So the next finding is around this getDutchAuctionStrike function. This function is supposed to be slowly decreasing the strike price of a particular vault from the starting strike to the reserve strike by the end of the auction. The auction duration is 24 hours, so we would expect the strike price to be starting strike at the beginning of the auction, and as the auction progressed, this price will slowly be reduced down to the reserve price the closer it gets to the end of the auction, which is 24 hours later. Now, the issue with how they're calculating the strike price at a particular time, they're actually scaling down the strike price from the starting strike to 0 at the end of the 24 hours, rather than scaling it down towards the reserve strike. Now, it sounds a bit confusing, as it usually does with explaining these math-based issues. So the best way to understand this issue, I think, is to just pull this code out into Remix and run through some numbers and look at the output from this particular function. So I've pulled out that function here. I've got the auction duration set to 24 hours, and I've got a helper function here just to return the block timestamp so we can generate some numbers. So go ahead and deploy the contract, and now we can call this a getStrikePriceAuction and see what it returns us. So I've made a spreadsheet here to simulate us reaching closer and closer to the auction end timestamp, and we'll run through some numbers into this function and see what it gives us back as the strike price. So we'll grab the timestamp in Remix now and put that as the start timestamp. With this timestamp set to the start of the auction, the end of the auction should be this timestamp, which is the start plus 86,400 seconds. And these are the values where we will be putting into the auction end timestamp parameter, just to simulate us getting closer and closer to that auction end timestamp. So for example, starting with the strike price of 100 and ending with the reserve price of 50. If the auction is 24 hours away from now, the return value should be pretty close to the starting strike price. And as we get closer and closer to the end of the auction, this is 23 hours before the auction ends, the strike price returned from this function will slowly go down. And as you can see, if you put in more of these values, the strike price will go lower and lower. And we would expect that the strike price would eventually reach the reserve price and stay constant at 50. Now, the issue with this function is it's actually going to return the strike price as 50 at a much earlier time than the auction end date. So you can see at hour 5, it's getting pretty close to the reserve price already. And by hour 7, it's already scaled the auction price down to the reserve price. And the price will stay at 50 for the remaining time of the auction. So to put it simply, the strike price that is returned by this function is scaling down much too quickly to the reserve price, when the seller may be expecting that the reserve price will reach to 50 near the end of the auction period. So the solution to this issue is to modify this function so that the price drops to the reserve price at exactly 24 hours. Which means scaling the strike price between the start strike and the reserve strike rather than start strike and 0. Now, the next high severity issue is around vulnerabilities in upstream dependencies, which I did find pretty interesting. So with this issue, you can create vaults with not yet existing ERC20 tokens because the dependency where they imported this safeTransferFrom function doesn't check a contract actually has code before making a low-level call. Now, when that happens, that particular call will always return true. So we're talking about another silent failure in the code which could result in empty vaults being created. So the import in question itself is soulmate utils safeTransferLib, which you can see is imported at the top of the contract here. Usually projects import the OpenZeppelin contracts because they're pretty much the industry standard at this point. However, this project imports the soulmate safe transfer library, which doesn't check for contract existence. So I've got the soulmate and OpenZeppelin safe transfer libraries next to each other so we can compare what the code looks like. Right off the bat, we can see a note here that none of these functions in this library check for token code at all. And comparing with the OpenZeppelin implementation, we can see a note here that this function does verify the target address contains contract code. We can see the check occurs in OpenZeppelin's addresses.sol contract, the relevant function here, which calls function call with value. Here it makes the low-level call on the target, similar to the soulmate implementation here. After that call, it goes to verify the call result from target. And if you compare with the soulmate implementation, this one only checks that the call is successful, and the OpenZeppelin one checks that it's both successful and also the target is a contract. Specifically, if you want to check if a target is a contract or not, it's done by checking account.code.length is greater than 0. So going back to our vulnerable code, since the soulmate safeTransferLib does not check for contract existence, this line may be successful even if no funds are actually transferred into the vault. This attack vector was also utilized in the Qubit Hack in January 2022. Do a Google search of the Qubit Hack and you'll be able to find some articles giving you a bit more background on this. Issues around contract existence check has occurred 5 times in previous audit contests. I have compiled a list here and I will leave a link in the description below for you to check out and read these relevant findings. These are the rewards that were paid out for each finding and how many wardens found that issue in a particular instance. In total, there has been 22k awarded on Code Arena for this issue, and the average reward was 2.2k. Now on to the medium severity issues. The first finding is around the set fee function. I would consider functions that can modify the fee a pretty low-hanging fruit finding, because when you're reading through the code, it's pretty obvious that a function is setting the fee in some way. And whenever that happens, you want to confirm whether changing the fee can result in an owner stealing funds from the users. And in this case, the fee is taken from message.value, directly reducing the amount of funds that a user will receive when they exercise a particular call option. So usually the recommendations around this are just fixing the fee, not allowing it to change by the owner, adding a time lock, or adding sensible upper limits to the fee that could be set. For example, you can't set the fee higher than 100% of the value. So as you can imagine, this issue around setting the fees is fairly common in past audit contests. Again, I have compiled a list here for you to check out in the video description below, and the total payout has been 22k with the average reward of 429 for each instance. The next medium severity issue is around an edge case where I think it takes a bit of creativity for you to find. So you can see in our favorite createVault function, a user can pass in an ERC20 token or an ERC721 to create a vault around that token. And when it does, it mints the user another token to represent ownership of that particular vault. Now, when it mints this token to the message.sender, this in itself is an ERC721 token. So a user can potentially revault that token into this createVault function again. And when they do that, it breaks a lot of the internal logic of the protocol. This finding was identified by 4 different wardens, and they each give slightly different examples of how the internal logic could break within this protocol. So I would recommend you to read through actually each of these findings by hovering over these duplicate reports and just go through some of the logic of how the protocol can break when its own token is put into a vault. In short, there could be scenarios where vaults can deceive users or users will lose funds. And as a mitigation around this issue, the code should check that this token address is not the Kali token itself. The next medium severity issue is around validating message.value to protect the users from sending too much ETH when they call the buyOption function. You can see that code checks that message.value is greater than premium. If the user sends more than is required by the premium, then that message.value will be lost and they will lose funds. So to protect users from their own stupidity, you should check that the message.value equals premium instead of message.value greater than or equal to premium. Validating message.value has come up 5 times in previous audit contests, and you can see in this audit contest in particular, the Kali one, it was found by 18 wardens and the payout was only $31. So it kind of goes to show that the competition in auditing has gone up quite significantly and the payouts are not as good as they used to be. So these are the stats for message.value validation, the average reward calculating to be $348. Now, I'll talk about these next 2 medium severity issues together because they kind of relate to each other in terms of they're both referencing support for exotic tokens that are usually not supported by DeFi protocols anyway. M4 is talking about rebasing tokens, where a token's balance of will increase over time based on the rewards accrued to that particular token. And M8 is talking about ERC20 tokens that charge a fee every transaction. So the person who's receiving the transfer will always receive a bit less than what the transfer amount actually was. These type of findings I've found came up over and over again in past audit contests, especially for this fee on transfer one, which is probably the biggest shut up and take my money finding I have ever seen and the most frequent one I've seen on Codearena. Usually the recommendations around these findings is restricting the support of the tokens in code and enforcing it, or properly documenting it in your docs that these tokens are not supported and you should not use them with this protocol. Support of deflationary tokens has only been brought up twice in previous audit contests, but the fee on transfer tokens definitely the biggest shut up and take my money finding on Codearena. I've compiled a full list here where you can find in the video description below. And you can see early on some of these findings are getting paid a massive amount in 2021 when there were not that many competition on Codearena in terms of auditors. But even so, payout has been pretty decent around fee on transfer tokens, even up to recently, where you can get a couple of $100s for mentioning it in an audit contest. But notably for our Kali audit, this was found by 25 wardens and the payout was just $10. So again, a noticeable drop in the pay due to the amount of competition now on Codearena. The total reward for fee on transfer tokens has unbelievably broken 100k, and the average reward being 900. But obviously keep in mind you probably won't be getting an average of 900 for mentioning this issue anymore because of the increase in competition, and it really makes me wish I discovered Codearena a bit earlier where you'll probably be getting a couple of $1,000s just for mentioning an issue such as this. The next medium severity issue is around overflows on the vault current expiration date. So the issue is when duration days is set to a number that is greater than 195, it will cause an overflow and cause the transaction to revert. Breaking this down, you can see that duration days is uint 8. And apparently this 1 days is treated as a uint 24. Now, I actually did a bit of research on this and I couldn't find any documentation that actually said 1 days is treated as uint 24. But interestingly enough, I came by this issue created by a fellow warden around this topic. And apparently 1 days is treated as a uint 24 because it's converted into the smallest type that can hold the value. So if you expand this expression out, it ends up being a uint 24, which I found was pretty weird and interesting behavior from Solidity. So since this is treated as a uint 24, this expression will be calculated based on a uint 24 multiplication. So for duration days larger than 195, it will cause an overflow in uint 24. The solution to this is cast the duration days to a uint 32 when doing this multiplication, so Solidity will use the higher of the two to perform the operation. The next finding is another one around setting the feeRate. Now, I'm not sure why this was actually separated out into its own finding because it's pretty similar to the other set fee finding we mentioned above, so I won't talk about it too much here. The next finding is an issue around griefing where a user can create a lot of empty vaults with 0 as the token ID or amount. Some background about this finding, there was actually a bit of pushback on the C4 Discord saying this is probably a bit too generous to be awarded as a medium finding, which I think I tend to agree with. So take it with a grain of salt because similar findings probably won't be judged as a medium in future contests moving forward. The next issue is a recommendation of using safeTransferFrom rather than transferFrom for ERC 721 tokens. This is a pretty low-hanging fruit, very common issue again in past audit contests. You can see it's found by a lot of wardens. The recommendation is around using safeTransferFrom for ERC 721s just to make sure that ERC 721 tokens won't be stuck in other contracts that don't know how to handle them. And the final medium severity issue is that the createVault function does not validate that the token type actually matches the token that is supplied as the address. This is actually pretty similar to the first high severity issue that we covered, but I think this issue doesn't quite describe the type of impact that the lack of validation will cause. So I guess this is to show that when you discover a vulnerability, you have to describe the issue properly to show full impact for you to be able to get rewarded as a high severity finding. And this is a point where CodeArena is probably going to be pushing towards more and more as we get more wardens onboarded onto the platform. We want to be providing good explanations with code proof ideally, so we can deliver higher quality reports to the sponsors of CodeArena. So that covers all the findings in the Kali report. Like I mentioned previously, I'll probably be doing these types of videos on a regular basis because it's kind of helping me as well to internalize some of these concepts as I go about explaining it in these videos. So just a quick progress update on my own bug hunting results on CodeArena. I'm up to 6.5k now on CodeArena this year, but haven't actually been doing very well in the recent contests. You can see I did drop to number 64 on the 60-day leaderboard now. I think in part due to my not so good performance recently, and also due to the new competition that has recently arrived on CodeArena. So that's my little update. Hope you enjoyed the video. I'll catch you in the next video.